More typically, you can't figure out a formula for the partial sums, and therefore you can't find the limit. Here's a second example. This second example is actually simpler looking than the first example. However, there's no simple formula for the partial sums. Let's write it out. So we're adding up reciprocals of perfect squares, 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus 1 over 5 squared, etc., forever and ever. Back about 300 years ago or so, 1700s, people really wanted to know what this equaled. They knew it converged. They were very confident that it did converge. But they couldn't figure out what it converged to. They couldn't figure out what the limit was. And the finding of the limit was called the Basel problem. Basel is a town in Switzerland. This is to find the quote unquote sum. They knew it converged. They just couldn't figure out what it converged to. It took the genius of Euler to figure out what it converged to. Euler spelled like that. Don't say Euler. No, don't say Euler. Say Euler. Or you could say Euler for short, or Euler if you want a little more flair to it. He figured out what it converged to. It's been programmed into Mathematica. What does it equal? You ready? Drum roll. Give me a drum roll. Pi squared over 6. Of course. What else could it be? No wonder they couldn't figure out what it equaled. Who would guess something involving pi? I don't see any circles. Amazingly, it does involve pi. What is that approximately? About 1.64493. I mean, you know, Mathematica can find lots of decimals here. About that. No wonder they couldn't figure out what that was. Euler did, though. He figured out it was pi squared over 6. And amazingly, he had an amazing technique. Amazingly, he used infinite products to figure out this infinite sum. I'm not going into details. It's very tricky. He figured it out. Shocking. It gets even weirder. He also figured out what the sum of 1 over k to the 4th was, and 1 over k to the 6th. They involve pi too. Pi to the 4th and pi to the 6th. How about 1 over k to the 20th? Involves pi to the 20th. Well, what about odd numbers? What? Zeta of 3. There's when it's odd, there's no simple formula involving pi. But when it's even, there is. Why? And what's the zeta? Zeta, called the zeta function, you could argue is the most important function in the world. Statisticians might argue, well, wait a minute, isn't that the normal curve, the most important function in the world? Some people would argue zeta is the most important function in the world. Why? Mathematicians would say because it's fundamental to the most important unsolved problem in math, called the Riemann hypothesis. The Riemann hypothesis, which I'll show you next week, involves the zeta function, but who cares? What's the Riemann hypothesis? The Riemann hypothesis is a very strange unsolved conjecture in math, whose truth is related to prime numbers, especially thinking about very large prime numbers and their distribution. And that's related to cryptography, which is related to keeping your internet transactions secure. Without the zeta function, no internet, or at least no internet commerce. Well, that might be stretching the truth. There might be some other ways to make them secure. But at least as internet transactions are currently structured, it's based on number theory involving large prime numbers, and that's related to the zeta function. This is astonishing in lots of ways.